I had complete freedom to just choose what to present, and I felt, oh, yeah. That I wanted to present quite a lot of different things, so I decided to give it a try. So I'll give a very broad overview. I will not go in depth in projects. If there's anything that I say that makes you curious about and I didn't give you enough details, you know how to find me and come and have a chat to ask for more information. Or obviously, you can also look at the papers. So if I manage to get PowerPoint to behave. So the general premise for my presentation is that, as I'm sure we all hear all the time, artificial intelligence and specifically machine learning got a lot of attention in recent years. In the past, maybe 5 to 8 years, there's been like a big jump in terms of what is possible computationally and amount of data that models can be trained on. So there's a lot of interest in the increasing efficiency and cost cutting that AI and ML systems can offer. At the same time, there's a lot of discussion also about the risks that can happen when things with AI ML can go wrong. And why can that be? Well, even though for some type of tasks we have very large data available, there are still situations where the data sets available are limited, or there are situations where, as I'm sure we've all heard, the data may be biased or there may be noise of some sort in the data. Some computational models still have limitations. Importantly, sometimes models get deployed in a context that is quite different from the one that they were designed in. And so the complexity and unpredictability of an application context can cause problems. And finally, one thing that I saw often in my own research is that often people have unrealistically high expectations of what AI and ML can do. So that's what is known as over-reliance. So the research I will present today, in broad terms, addresses the question of how can we design interactions and user interfaces around AI ML systems to make them usable and useful despite possible technical glitches and limitations. My perspective is that I want to be able to keep users ultimately in control, so that even when a system may make mistakes, people can get things right if they can understand what's going on. That is tricky because these systems are very complex. So we observed in a number of studies that often people have misconceptions about how these systems work. And we also identified some cognitive biases that people have around this kind of systems. I will talk a little bit about that later. So a more refined question is also about like which kind of things does it make sense to show on the UI? Which kind of things do we show on a UI help people make sense? And which kind of things instead may actually confuse people, like we saw in some of the studies that I'm going to present. Mark already said a few things about my background, but I got a slide. This is because I feel that this is very much kind of a reintroduction of myself at UCLIC, given that many people joined over the past few years. So I started studying electronic and telecommunication engineering at the University of York. And then I went to work as a researcher at Media Lab Europe, where I was working with Rebecca Allen, who is a professor of design and media art, but she's also an artist. And actually, she has 2 pieces on show at Tate Modern right now in the Electric Dreams exhibition, which was very exciting to see a few weeks ago. With Rebecca, I was working on augmented reality and some elements of virtual reality and wearable computing. Then the lab in Dublin shut down. I was one of the fortunate survivors to move to the lab in Boston, where I continued to work on wearable computing and also started doing some work on tangible interfaces, low-cost tangible interfaces. I continued that at EPFL, back to Europe in Lausanne, Switzerland, where I did my PhD with Jeffrey Wang, my advisor, who is an architect, not software architect, but actually brick and mortar or like glass and steel and interactive surfaces kind of architect. So there I also worked on sort of urban computing and like mobile HCI and all of that. After the PhD, I started as a lecturer in Southampton, and from there I joined UCLIC in 2016. Part of the reason I want to mention this is, first of all, to joke with Anisha about positionality statements and the fact that my technical background, I feel, is something that stay with me. I'm really keen on prototyping and putting prototypes in front of people rather than observing things that someone else built, even though I end up doing often a mix of the two. So this is the outline of my talk, having just gone through some introduction. I will have two strands. First, I will present some more exploratory work I did around AI systems that are meant to support people taking advantage of or making the most of renewable energy in a domestic setting. And then I will present a small collection of studies that instead are more constrained and focus on specific UI features or specific phenomena around AI ML systems. So let's see. My interest in interaction with AI, human interaction with AI, started in Southampton. There I was working in a group researching autonomous systems. An autonomous system is basically a piece of technology that can monitor data on our behalf, process that data using some form of a pattern recognition or machine learning, and then autonomously react to that data. So a sort of airplane autopilot falls under that definition, as well as drones of the sorts. But the kind of systems that I got interested in are instead things like smart appliances, like smart washing machine and smart thermostats. On the slide, you see the Nest, which is one of the first commercially successful smart thermostats. So these are autonomous systems that are meant to be used in situations where the data is not a central part of what people do. Like an autopilot, someone will have been trained to use. Nobody will ever read the instruction manual of their washing machine or their thermostat, or very few people would. The smart thermostat, I think, is an interesting example because it combines explicit user input, people adjust it, with sensor data, temperature, and in some cases also presence sensors, to then actuate the heating or air conditioning and turn the temperature higher or lower or completely turn off the system. Unfortunately, it seems that smart thermostats do not work as well as some people expect. In a series of studies that Ryan Yang and colleagues from the University of Michigan did around the time when the Nest became popular, revealed that some of their participants kept the air conditioning on 24/7 because they expected that the thermostat would be smart enough to switch the air conditioning off when they go out, but it turns out that that is not. And in terms of energy consumption and sustainability, that is obviously an issue. I find it interesting and funny that I'm not sure when the first smart home was proposed, but already in 1922, which is more than 100 years ago, Buster Keaton made a movie called The Electric House, which basically makes fun of essentially a smart home. It's a home where things move out of their own will and things can go comically wrong. But exactly because it's easy to imagine how things can go comically wrong when you delegate agency and you start to have actuation in the home, I think that makes it a really interesting and challenging area to do HCI research. Can we design interaction around the system so that when they work well, we take advantage of it, but when they don't work well, we regain control? The initial studies I've done in this context were around renewable energy, and again, domestic in a domestic setting. Again, we're all familiar with the idea that we should use as much as possible energy coming from renewable sources, such as the wind or the sun. However, living in London, we are all very familiar, except for the last week, with the fact that it's not always sunny and it's not constantly windy. So these sources of energy are intermittent. This means that sometimes we may need to, or we will need to switch back to fossil fuel. However, we need to think about strategies to shift as much as possible of our consumption to periods of time where renewables are abundant. One strategy that has been discussed for a long time in the energy literature and now has been turned into practice is to provide financial incentives for people to consume more when energy comes from renewable sources. The idea is that of dynamic pricing, basically make energy more expensive when it comes from fossil fuel and make it cheaper when it comes from renewable sources. You can also think of it as a carbon tax. And it's not the only mechanism, but it's one that I found very appealing and very interesting to work with. So this means that before I go and turn on my washing machine to do my laundry, I should check what is the current price of energy. I should also look at the forecast. Is it going to become more expensive or is it going to become cheaper? And then make a rational decision about whether I should turn the machine on now or wait for a few hours. Well, that's obviously a joke. Nobody will want to have to worry about that in addition to the chore of washing your clothes already. But that's the kind of thing that I think we can easily imagine delegating to an AI system, right? The system can monitor the energy market, can monitor my consumption and try to predict it, take into account the weather forecast, and therefore understand the generation forecast. And then it can switch me to a different supplier, or it can charge a battery or turn my washing machine automatically and so on. So to study these kind of applications, and as I said, I'm keen on doing studies where we deploy prototypes, we had to devise an experimental trick to simulate this kind of future scenario where energy prices are dynamic. Essentially, we did that through financial incentives. So when participants start one of our studies, we give them a budget, which can be 30 to 100 pounds, depending on the duration of the study. And then we install electricity consumption sensors in their homes, so we can see in real time how much they are consuming. And we use that data essentially to create our own energy billing system, which we can base on this dynamic pricing that is based on publicly available information about the availability of renewable energy. And we run it against the budget that we give participants at the beginning. So essentially, in this way, if I participate in the study and I use energy mostly when it comes to renewables, I will see my budget going down more slowly, while if I use energy when it comes from fossil fuel, I will see this budget going down faster. At the end of the 2 or 6 weeks of the study, we give participants in cash what is left in the budget. So that is, on one hand, a bit of a playful thing like a gamification, but it's also a bit of a mimicking what it would be like to make a saving on your monthly energy bill. So we designed and prototyped 3 different systems against this scenario. And in the interest of time, I will present all 3 systems first and then talk about the findings and how we deploy them at the end. The first system is called Tariff Agent. It's an autonomous system, or an agent that monitors and predicts the individual household energy consumption as well as the energy market, and tries to match the two, tries to find the most convenient supplier or the most convenient tariff for the user. We play this in fast forward, while in reality you will be able to switch energy supplier on a monthly basis. In our study, we allow people to switch on a daily basis. The system has a web UI, which you see on this slide. Through this web interface, you can choose what level of agency to give to the system. So you can say, just send me an SMS when you think I should change tariff, or automatically switch me to the tariff that you think is most convenient, but send me an SMS so that I can undo the change if I'm not convinced. Or you can put sort of like set and forget, just like take care of my tariff. I don't want to know anything about it. Don't bug me with SMS messages. As I mentioned, the system tries to predict my future consumption, but you can manually adjust that. So for example, if you know that tomorrow you're not going to be at home, you can tell the system that tomorrow you expect your consumption to be a lot less than usual. The second system of this small collection is called Agent B for battery. In this case, it's an agent that charges a battery when energy is cheap, so that then people can consume energy even if the market price is high. For various reasons, we decided to focus on laundry. So we simulated a situation where the battery is only connected to people's washing machine. Batteries tend to leak energy over time. So this means that to optimize this, the system needs to take into account when energy is cheap, but also it should charge as late as possible compared to when you want to use the energy. So for that, we designed an interface to essentially allow you to book your washings. You start by selecting the type of program that you want to run, which determines how much energy you need and the duration of the program. And then the system calculates prediction of how much it would cost to run the load of laundry at different times over the next 7 days. Again, remember that in this case, price is aligned with carbon. So high price also means high carbon. So green means cheap, but it also actually means green energy. And in this case, you can see that perhaps at the beginning, the system doesn't have enough time to charge the battery, so the price is quite high. However, after a while, the price becomes lower, and then later on, it gets expensive again. Forgot to say, this is basically calendar. So each day, each column corresponds to a day, and these are like slots, like in your Outlook calendar or whatnot. The idea is like you click on one of these slots, and then you get a sort of finer grain selection. It confirms the price, and then when you book it, it will show up in the calendar as if it was a meeting. So the system also includes a dashboard page, which you see on the slide, and this shows information about the next scheduled booking, how much charge is stored in the virtual battery, the budget, how much you have available, how much you spent so far, and for accountability, a list of washings that you've done, so like you see where your budget went so far. The third and last system of this collection is a smart thermostat. Here we got a bit more ambitious, so we used again the simulated pricing based on availability of green energy, but we actually linked this to a Raspberry Pi thermostat that we installed in participants' homes. So the temperature in participants' homes was actually controlled by our intervention. And essentially the idea was turn the heating a bit lower when the price goes high, taking into account the participants' preferences. We had three versions of the system. The manual version has a set of sliders that users are supposed to use to basically set their trade-off between price and temperature. In the second version, which we call direct learning, instead we use a Bayesian inference algorithm to dynamically learn the preferences. So whenever people press on the plus or minus buttons, the system takes into account the current price and updates a model. Now, this kind of models essentially have inertia. So at the beginning, it will give a lot of importance to your input, but after it gains sort of like a certain amount of information, it will become slower to update. Also because these algorithms essentially consider user input as noisy, which is interesting from an RCI point of view. But basically, we call this the direct learning option because this interface shows you really what the learning system is doing. So this means that after a while, to see a change, you will need to press the plus button a lot of times because you will see that the system is actually ignoring you for a lot of the time. In contrast, the indirect learning is more responsive, but only for a short time. So when you press the plus button, you change the temperature only for 1 hour, and then the system after 1 hour reverts back to the learned model. All the systems I presented, not just the thermostat, but also the washing machine one and the tariff agent, in addition to having a web UI, which I showed before, can send users text messages or emails for things like reminders of the bookings or notification about switching tariff, and also daily status updates. Today, you spend so much on energy and you consume so much that was renewable or not, et cetera, et cetera. We prototype the systems using a combination of web technology, HTML, JavaScript, et cetera, and off-the-shelf or custom-made hardware, the sensors that we install in participants' homes. This means that we could quite inexpensively deploy the systems in 10 to 30 homes per trial. And we ran 4 trials for this collection of projects, which lasted between 2 to 6 weeks. We collected data through semi-structured interview at the end, sometimes also at the beginning, but we also recorded participants' interactions with the system, as well as the sensor data to see like how the temperature in their home changed and like whether the consumption, the electricity consumption changed in any way. The key findings from the studies show that people engaged with the autonomous systems, even beyond or a lot beyond our expectations. Participants integrated the systems in their everyday practices and provided quite a lot of input, manual input, to improve the system performance. Everyone liked the text messages as a way to keep an eye on what the system is doing, like maintain awareness. And these messages also served as a way for participants to see that the system was doing work in the background. It was interesting to see that sometimes participants overestimated how smart the system was. Even though at the beginning we told them that, for example, the tariff agent system only looks at data from yesterday to predict your consumption tomorrow, in the interviews, people told us things like, yeah, at the beginning it was not working very well, but then over time it learned my patterns. And I was like, no, it doesn't. And similarly, another surprising point was that participants felt very much in control. Even though technically they are delegating agency to a system, we heard things like, yeah, I save money using this, rather than the system saves money for me. And finally, this experimental trick of linking reward with sensor data worked really well. Again, beyond our expectations, even though we told participants that this was mostly simulated, and in fact, the wind data that we use in some of the trials was recorded months before the trial took place. in the interview, people told us things like, yeah, on that day, I saw that it was very windy outside, and so I thought it would be a good day to run my laundry. So they really got immersed into this illusion. Just to give you a quick example from the things that we saw from the quantitative data, in the washing machine study, out of 155 washes that participants did over the trial, 77% were booked, which I think is a very large proportion. And the bar chart shows how punctual people were. So the first bar indicates that 60% of the times, people did their washing within 10 minutes of the time that they booked it. And if you put together the first and second bar, 80% of the bookings were done within half an hour of the time that they were made for. So again, this suggests that participants took the trial and the system quite seriously. More information obviously is available in papers, but I'm putting this up so that I remember to acknowledge my collaborators. This work was done with colleagues and PhD students at the University of Southampton, as well as the University of Nottingham and the University of Zurich in Switzerland. And the work was partially supported by an EPSRC program grant led by Nick Jennings in Southampton. While the studies that I presented so far focus on individual homes, I will now present some more recent work that looks at energy communities as a way to think about supporting people make the most of renewable energy beyond the individual level. And this work was supported by an EPSRC project called Beyond Individual Persuasion, which is in collaboration with UCL Anthropology and the Energy Institute with Kirill and Yuria, who is now at King's. So what are energy communities? Energy communities are basically initiatives that try to promote the local production of electricity from renewable sources. And there's a very strong push politically for them, especially in the EU, where there is an expectation that by 2050, half of the EU renewable energy will be generated in energy communities. One practical example is neighbors sharing a solar panel. Why would they do that? Because it's cheaper to install. They would share the price. And maybe because it's easier to make the most of the energy that is generated by the panel. The challenge with this kind of scenario is that intuitively, when we want to make the most of a solar panel, we should all shift our consumption towards the middle of the day, because that's when there is the most generation, because when there is most solar radiation. However, if we all do that at the same time, we may end up in a situation, which is kind of illustrated by this picture here, where our aggregate consumption will overshoot the generation. So essentially, we need some way to coordinate. So to address that, and very much as a probe, we designed and prototype what is essentially a shared calendar. Again, the same as some of the designs, similar to the designs you saw before. Here, each column corresponds to one day of the week. This is today, and these are the next few days. The orange bars, well, they're orange on my screen. Here, they're not very orange. These bars represent the forecast of solar generation. And through the system, people can book their consumption. So they can say, tomorrow, I'm going to use the washing machine at this time. And then those bookings show up as rectangles on this UI. And you can optionally say, I'm flexible about this. So if someone else needs to use energy at this time, I can rearrange that and do it at a different time. So again, this is basically a way to help coordinate. We deployed this using a very similar approach to the previous projects for 3 weeks with 15 households in 4 groups. So like we had each group simulating an energy community. Again, this was based on real sensors, sensors collecting the real and real-time consumption of people, but the solar panel was basically simulated. Participants engaged to various extents with the system. They made from 4 to 61 bookings per household. 3 out of the 4 groups improved their solar consumption compared to a baseline week that we measured at the beginning of the trial. And as before, we did semi-structured interviews through which we learned that the bookings worked as a way to coordinate, not only across households which are members of the solar community, but also within the household. And in general, the calendar worked well as a sort of a planning resource. Like the calendar worked well as a calendar. One thing that was interesting is that even though people practically communicated, they didn't feel that they were communicating. So they told us that they didn't really feel a sense of community. I can't tell you much more about this because I want to cover a few other things. I should mention that Solar Club, in its current form, does not involve any AI. So it's a bit of an exception compared to the rest of the projects that I'm presenting here. But I decided to include it because there is some current and future work that I'm doing which builds directly on it, which I wanted to share. So one project is called Solar Chat, which is in collaboration with Matthias Giudici, who was a PhD student at UCLIC visiting from Milan, and is a supervisor in Italy. Where basically we replaced the graphical interface of Solar Club with a chatbot. We did this for 2 reasons. One is because one of our project stakeholders commented on the fact that not everyone may be interested or inclined to engage with our visualization. And secondly, because we wanted to explore how far we can go with a text-only interface, because a text-only interface is something that you could render on a voice-based UI, which has obvious accessibility benefits, but it can also be convenient if you can put it on something like an Alexa or the like. I can't say much more because that work is being prepared for submission, but if you're curious, happy to have a chat. And the other project, which is work in progress, is called PowerShift AI. This is a fellowship that Kirill is leading, funded by AHRC. And it's in collaboration with the Microsoft Research in Seattle, as well as, again, Uria at King's and Mirko Mussolesi, who is upstairs in CS. So in this context, we are looking at applying reinforcement learning to control the charge and discharge of a battery in the context of the solar community. So if there is a battery connected to the solar panel, how do you optimize that, and how do you forecast people's consumption and so on? We are training a reinforcement learning model on the data that we collected in our previous deployments, and we are hoping to deploy again over the next few months, with fingers crossed as usual. So in parallel to the field studies I've just described, another strand of my work uses a more constrained approach, lab studies or online studies, to focus on specific features of the UIs around AI and ML systems. One example is a study that we did around ML confidence. So some algorithms that recognize objects, for example, so some pattern recognition or ML algorithms, can produce confidence data. So that is a value that indicates the degree of certainty in the result produced. Is it valuable to show this information to users? If we go back to the idea of the smart thermostat, what if the smart thermostat told you, I'm 70% confident that you're at home, so I'm turning the heating on? What if instead it told you that it was 60% confidence, or that it was 90% confidence? Does that make a noticeable or measurable difference? To answer the question, we shifted away from smart thermostats, and instead we focused on much simpler tasks. Because the way that people interact with the thermostat will not be influenced only by the UI, it will be influenced by a very large set of factors. So instead, we wanted to sort of zoom in and sort of simplify as much as possible. So we designed a study around around two very simple micro tasks. So these are the kind of tasks that people do on Mechanical Turk for pay. We had two tasks in the study. One was to fix grammatical mistakes in a text, so basically proof checking. And another one was to check and fix possibly the output from a handwriting recognition system. Critically, the first task is a completely manual task, while the second task is one that is around an AI system. So the main dependent variable in our study is the proportion of tasks of AI type versus manual type. Participants could do as many tasks as they wanted of whichever type they wanted. So if we manipulate the UI of the AI system, will we see a difference there? If we make the UI better, will participants use the AI system more? It's kind of an adoption measure in a lab setting. And specifically, we manipulated the UI of the AI system around confidence information. So in one condition, this study was between groups. So one group of participants had color coding in the UI from light blue to dark blue. There were, and also text labels with 5 levels of confidence, from very low confidence to very high confidence. The other group instead had the same, except that the color and the labels went away. The results show that confidence does make a difference. The participants who had the confidence information available did a higher proportion with statistical significance of tasks of the AI type. We also observed that there is a measurable difference between things that are labeled as very high confidence and things that are labeled as very low, and medium. But there is no difference within this group. So from a UI design point of view, this is good news, because this means that, like, if you're working with an algorithm which makes confidence information available, you should present that to users, because people can make sense of it and they can change their behavior using that. Later on, we did a similar study around AI explanations. As you probably heard, there's quite a lot of work going on around AI explainability. That is because some of the most popular models, ML models used now, are extremely large and growing. They are trained on enormous amounts of data, and they involve a very large number of parameters. So being able to understand why a model would give you a certain output is very hard, if not completely impossible. So people have been developing sort of additional algorithms that analyze what the model does and tries to post hoc explain why the model gave you a certain output. One popular way to display this explanation is through so-called saliency maps or heat maps. There is an example on the slide. So on the left, you see an input picture, and on the right, you see a heat map. So the pixels in red are the ones, well, again, it's red on my screen. You can barely see it here, sorry about that. Basically, these pixels are the ones that are considered to be most important for the system to classify this image as containing a horse. So in this case, you can see that actually the head of the horse, which is what perhaps a person would use, is not at all used, but instead the model seems to, according to this explanation at least, seems to pay attention to pixels on the legs and around the torso of the horse. Do this kind of explanation help people in practice? We ran a study to answer that question, and we found that to a certain extent they do. So when saliency maps were shown, our participants' performance was significantly, was higher with statistical significance than when heat maps were not shown. However, I should also emphasize that performance was not high overall. So in our task was a binary task. People had to answer questions, oopsie, about whether we should be back in action. Okay. Let me. Okay, I'll leave with that thing now. So I was saying, in our study, the task was binary. People had to answer whether they think that the model will recognize an object, say a horse or a car here, yes or no. So if you flip a coin, you would expect that you will be right 50% of the time. Instead, with explanations, our participants were right 60.7% of the time, which is better, but not like, wow. And without explanations, they are still better than chance, but like 55% rather than 50. So it's interesting, but I'm not excessively excited about the effect of these explanations. I should say this work was in collaboration with Nadia, because it was part of the PhD work of Ahmed Al-Karawi and Martin Schussler. Ahmed we co-supervised. I'm running out of time, but I hope I will have time to tell you about another PhD student who's actually here. This is another study in which we did a user evaluation on a system that we did not develop. I forgot to mention the explanation that I showed you were not developed by us. They are from a group in Berlin, and they were considered to be the state-of-the-art explanations at the time. So similarly, we got interested in a deep learning model, which was developed by a collaboration of Google DeepMind and Moorfield Eye Hospital. This is a model which takes as input OCT scans, which are medical scans of the eye. And then the model predicts whether, based on the scan, the patient is likely to have a retinal disease or not. What made us very interested is the fact that the model also produces a visualization, which is essentially an annotated version of the medical scan. So we wanted to understand whether, and we expected that this visualization would help users. Who are the users of this system? It's optometrists. Optometrists are primary care health professionals who essentially work in the shop where you go and buy prescription glasses. So they will be able to, and they are trained to do an eye examination and prescribe you the glasses. But if they find anything more serious with your eyes, they will refer you to an ophthalmologist, possibly in a hospital. OCT scanners are becoming like cheaper and cheaper. So many high street optometrist shops will have OCT scanners in them, but the optometrist generally will not have had a lot of training on this kind of scans. So the value proposition of this model is that it can help optometrists make sense of these scans and take better decisions about whether to refer their patients to the hospital or not. So to test whether this was the case and the effect of visualizations, we ran a study where 30 optometrists participated, and the study had 3 conditions. This was a within groups study. So in one condition, participants saw 10 scans without any AI information. In the second condition, they saw the scan plus the diagnosis only. So basically the information whether the AI model thinks that this scan corresponds to a disease or not. And in the third condition, they see the same plus the visualization, which is the annotation of the scan. So each participant saw 30 scans, 10 per condition. They were balanced and matched. I should emphasize that we cherry-picked scans for which the system does not work very well. So while in the testing that was published for the system, the accuracy is 94.5%, about 1/3 of the scans that we presented to our participants are such that the system went wrong on them. So it's not representative, but we felt that this was the most interesting data because we felt that that's where the visualization is can be expected to make most of a difference, kind of in these edge cases. To our surprise, it didn't. In fact, we found that, as you can see from these bars, in the no AI condition, participants performed better, like around 80%, than when they also saw the AI diagnosis. And they did even worse when they saw the AI diagnosis and the segmentation. So this seems to be misleading. We looked more in detail, and we saw that in the cases where the AI is correct, the visualization seems to mislead our participants. So they accept fewer of the correct suggestions that the AI system gives them. While there's not much of a difference in terms of when the AI is incorrect. So this was work that was done by Josie, who I co-supervised with Anne and Konstantinos Balaskas, who is an ophthalmology professor at Moorfield. Speaking of digital health, that's a topic that I'm very excited about. I think that like the impact of AI ML systems in digital health is really important. We see that there is a lot that can go wrong. Like again, in this case, if you think about the idea in abstract terms, having a system that helps primary care worker make sense of medical images sounds like a great idea. Then you test it in practice, and then it's a bit less exciting maybe than we expected. So I wanted to share briefly that we recently started a new project with Jeremy, as well as with Evans Mazomenos, who's the PI in medical physics, Dan Stoyanov in CS, and other Francis, about the use of AI to improve training of robotic surgery. So it's well understood that robotic surgery has many benefits compared to its traditional counterpart. But one bottleneck is that we cannot train surgeons fast enough to operate through this robot. So Evans, the PI, has been developing AI models to automatically give feedback to people who are learning to use these robots. And we are going to look into how do we present this feedback and try to sort of quantify the effect of this. How are we doing for time? Okay, we are almost out. Just very quickly, and then I will close. So in the previous study of like our evaluation of deep learning around eye care, we saw that showing additional information around the AI system can actually have a detrimental effect for users. I think that this is not too strange because the systems are extremely complex. So we found that sometimes users will develop an expectation or a mental model of how the system works that can be completely incorrect. And we ran a study where we saw that what we show on the UI can make things even worse. And we found that there is a cognitive bias possibly there. So I'll just show you that and close. So we ran a study where in one condition, participants saw what you see on this slide. On one side, a piece of handwritten text in a language that probably for most of you is foreign. And on the right-hand side, the sort of a digitized version of the same text. So like there's a handwriting recognition system. This is the input, and this is the output. This is the no animation condition. Instead, we also had an animation condition where this is what participants saw. So one word at a time is highlighted on the input side, and correspondingly, one word shows up in the output. We told participants a cover story. We told them that we were evaluating two handwriting recognition systems, and we wanted them to tell us how well they work. But instead of asking them which system works better, we asked them which system do you think most people will choose as the one that works better? Because we wanted to make sure that they think a bit harder about the question. And we told them that at the end of the study, we will count the responses, and if you answered in the majority, we will give you a bonus compared to the, you know, the typical reward. And what we found is that both in the lab and when we replicated the study online, there's a clear effect where people think that the animation condition, in the animation condition, the system works better, makes fewer mistakes, and they go in great length about telling you, yeah, it misrecognizes this letter and that letter. The two systems were completely the same. It was Wizard of Oz. There was no system whatsoever. So it's clearly a bias. Why is that? At the beginning, I thought that maybe it's because the system highlights the word left to right one at a time. And so maybe people think that it's human-like. So we did a study to check that. We're using the animation that you see here. So in this case, again, it's the last two lines, but the words appear in a random order, which is clearly not how a person would do it. And to my great disappointment, the effect was still there. In the animation condition, people think, yeah, that works better. So we found that it seems to be something to do with the mental model. Almost by chance, we noticed that if we ask an open-ended question before the task, we tell people, you're about to evaluate a handwriting recognition system. How do you think this kind of systems works? And they had to write the answer in a text box. This was an online study. Then the effect goes away. So we did another follow-up to sort of double check what was going on there. So we created an alternative animation, which you can see at the bottom of the screen. So instead of highlighting the word like before, we box it and we invert the color. Then we did a study where we created an explanation, or really a description of how the system works. And so we had two animations and two descriptions. Like the system works by highlighting each word and then detecting it, something as simple as that. Then half of the participants saw an explanation that was matching the animation, and the other half saw mismatching explanations and animation. And you can see that when the two are matching, the effect is there, and when the two are mismatched, then the effect disappears. Nobody mentioned the animation, or hardly anyone mentioned the animation. So this seems to be an unconscious effect. Like people maybe get this sort of like fuzzy, warm, fuzzy feeling. They're like, oh yeah, I kind of see that how this is possibly working, or I have no idea how this is possibly working. So they feel less trustful for that. I don't have time to tell you about the last project because I went badly over. But just in summary and to close, I presented a small range of field trials and control studies around user interaction with AI and ML. The takeaway message is that I think that reasoning around how do we design interfaces around these systems is particularly tricky. If you take away one message, that's the one that I would like to take. So I think that there is a lot more work to do as an HCI community in this space. And I think that it's really important to get hands-on, to train models, show participants things that really come from ML, or at least realistic simulations of that. And with that, I'll be happy to take questions if we have time, or again, you know where to find me.
Questions?
About the
yeah.
Did you try with some more trained people, practitioner rather than the optometrist, or do you think you would see the same results?
That's a very good question. Because I was trying to cram a lot of things, I didn't give you the full story. We actually had 30 participants divided into two groups. Half of them had up to 2 years of practice, and the other half had more than 2 years of practice. And we did not see any effect there, other than people with more experience were more confident in their own diagnose it,
Gotcha.
but no interaction with the AI.
But we're all optometrists.
Yeah,
not...
so the question about whether it would make a difference for ophthalmologists, like someone who is more specialized training, is a good question. We didn't explore it also because, again, this system is specifically sort of like marketed for this population. So that's the one that we were interested in. But it's a very valid question about whether others would equally get misled. Again, I should emphasize that these are edge cases. So if this gets deployed, this kind of cases would appear very, very rarely.
Yeah. I'm asking because I saw, and I don't have any knowledge in that other person's eyes. When I went to the hospital, and so he started to do many different measurements on that similar image there, and the young trainees wouldn't do it. And I was telling her, you need to look at that. And when I go to the optometrist, she kind of refused to say anything and look beyond that. So there is, one that's developed their own measure that may be very different from the visualization. And I wonder if, it's exploring here. As you say, there is a lot of work. I think, what do we visualize could be. Because what we're visualizing now is the output, direct output of the AI. I suppose it's similar to the horse one. I don't know. And
yeah, it's not exactly the same as the saliency map.
Yeah.
But definitely it's interesting because, again, there's like the interaction between what is the role of the person that you're interacting with, what is their training, and are we putting them outside their comfort zone by asking them questions that they know they're not trained to answer, so they would not want to mislead you in giving you an answer. Again, I can see how the argument that, like, AI may help in that is really a convincing one. But this, I think, is one where we also found that some of the cases that we selected were tricky because the ground truth is a bit ambiguous. And even experts had disagreement about whether this clearly is a case of this or a case of that. Again, I should also emphasize that our study was very much kind of like in vitro, in that in reality, when people look at these images, often they would also have other information about the patient. They may have the patient in front of them, while in our study, they only had the scans because we want to sort of keep everything fixed and just look at the effect of the...
But referring to the scan, so I think that the head of the group had developed his own measure and started to use the system in a way that made sense to them. So I wonder if one direction here on addressing the point you were saying of explainability is really work closely with them to see what model they have independently of the AI, because here we are thinking how the AI present the reasoning, but the clinician has developed their own reasoning and how, create something much more interactive rather than a static visualization.
Yeah, I agree.
Just something. I remember saying, no, you need to measure that. I had no idea, but I saw the other measuring and knowing something about interfaces, I was noticing what he was doing.
I can't say I understand the medical detail of what you're hinting at, but in general terms, I completely agree that I think that doing more work across disciplinary boundaries is critical here, because I think that, and this is something that came up in the discussion of that paper, a lot of AI models are obviously coming from the ML academic community. And in the ML academic community, the currency is performance in terms of accuracy, and they don't necessarily think about what are the user requirements. So I think that, like, thinking about how do we design systems, not necessarily just so that they get the highest accuracy, but so that they are most useful to people then using it in the field, is important. And I think it goes to the issue of are we building AI to replace people, or are we building AI to support people? I argue that we should, in most cases at least, build AI to support people. But building an AI to support people may not necessarily be about getting the highest score in those terms. Yeah. But obviously in conferences like NeurIPS, et cetera, that is the currency. So I think that this is work that needs to be at the intersection of the two communities. And I think you start to see some of work in that space at CHI, but it's tricky because I know probably as well as you how difficult it is to find PhD students, for example, who are interested in HCI, but also are sort of daring enough to deal with the ML and the sort of technical complexities that come with it.
Follow-up question there would be, how would you design any tests around how to make these ML models useful? If you think about going beyond accuracy, do you have any thoughts on how to incorporate that? Because it could be a benchmark. And
well, I don't think it is. I think that like, I mean, this is obviously something that being embedded in a sort of a AI group, like, you know, became painfully clear when the students of my colleagues make a mistake, they run the simulation again overnight, and the mistake is fixed the following day. If you made a mistake and you need to rerun the study with participants in the wild or even in the lab, now with Prolific is better. But like collecting HCI data is a lot more time consuming and painful than running simulations. I mean, there are probably sort of like special cases where smart tricks may be possible, but I think that in most cases, I'm not convinced that there are shortcuts. I think we need to like, you know, do the dirty work of recruiting people, putting stuff in front of them, and then sort of measure and see what happens. I can't think of a sort of a automatic test benchmark that you can create with that, except for maybe some edge cases. And then we kind of go back to the question of like, is design an art or a science? Do you start to get intuition? We need design patterns. The thing that is tricky is that there are lots of design patterns already published for interaction with AI, but I'm not convinced. I think that a lot of those design patterns are not grounded in enough research, because I don't think that there are that many studies there. Yet I remember like in 2019, Microsoft published like a set of guidelines for like how do you design around AI, et cetera, et cetera. It's tricky, right? Because there's obviously a lot of money there, which is great, but it's also not great because then everyone is like telling you, we solved the problem. When if you look closer and closer, maybe it's not actually completely solved just yet.
How do you think, or how do you think all of this is affected by AI literacy of people, and like over time, maybe what have you observed how mental models change?
It's a good question. I've been wondering about that a lot because some of the studies you might have noticed are a bit old. They're like from 2013, 2014. But I was surprised that actually the last study I didn't have time to present, we ran last year, and we found similar patterns. So we found that participants overestimated what the AI was telling them, and they assumed that the AI was correct. And if anyone made a mistake, it was the participant who made a mistake. So I didn't reflect on it before your question, but it's actually interesting that I would have thought that, you know, after all the exposure that people had to AI in the past few years, that there may be a bit of a difference, but actually there isn't. And again, if you think about how large language model chatbots work, they are very assertive. So I can see that they are definitely not particularly helping in that. And anecdotally, I was also very surprised that like some of my first year undergraduate students were a lot more clueless than I expected about how ChatGPT works. Not CS students, this was like another cohort. But I would expect that at this day and age, any first year student at UCL would have some idea of how ChatGPT works. But I guess that's like, I need to get off the ivory tower and the sort of a Stack Overflow tribe. But thanks, that's a very interesting question.
One final question.
Hi, thank you. Actually, I'm very interested about the experiment results in the OCT scans about actually the explanations provided by AI cannot like help physicians to diagnose the disease. So just ask for some clarification. In that experiment, the pure AI performance is actually worse than human physicians. Is that right?
Well, I think you need to take into account that we cherry-picked cases which we knew the AI would be wrong on. So I think it's difficult to draw a comparison in those terms. Basically, we took a data set of scans and we manually cherry-picked the ones where the AI model went wrong. So the AI results were wrong by design. So I don't think we can compare in that sense, because we basically wanted to look at edge cases, troublemaker cases, because this is one, and I mean, I could give another talk about methodological challenges. Because AI systems are work very well, one tricky aspect of design studies is that having help from the UI is relevant mostly when things go wrong. If the system is working fine, then you just let it be. So if you do studies in the wild, if you do studies that are like realistic, it may take you 2 years before a participant sees a mistake. So we need to be very careful in sort of designing the studies in a way that we show the most problematic cases to participants. And so in that context, we were not looking at the comparison between human performance and computer performance. We deliberately chose situations or like data points, scans, which were tricky. And we saw for these tricky cases, does the visualization help or not? And the answer was no. Yeah.
Oh.
I'm not
So
sure.
It was seeing when the person improved rather than the system get it
Yeah.
right.
Yeah.
Because I feel like I have a feeling like if we know that AI is kind of perform better than human physicians, then this question would be like we under reliance on AI instead of over reliance. Because if we always rely on AI, the accuracy could be improved because the overall performance of AI is better. Perhaps it's perhaps because we are suspicious about AI and we don't adopt their suggestions sometimes. As a result, we make more mistakes. Is that possible?
Well, it's a very good question. So I don't know what your background is, but I think that the one tricky thing is that AI systems these days very often are trained in research conditions. And when you transition from research conditions to real world deployment conditions, it is well known that there are big gaps. There are questions of responsibility. Are you suggesting that we should replace a doctor with an AI system? Then if that makes a mistake, who do we sue? The company who made it, the company who runs it, the company who trained it, the company who gave it to you? It's a tricky question. So again, I think that like there are some philosophical issues there, but from my point of view, I think that we need to look at the performance of the social technical system, which includes the people and the AI. I would also argue that spitting out a diagnosis is part of the job of a doctor, but not the only job. And actually, there's a lot of like human-to-human interaction there, and there's plenty of literature around that. I think that like looking at it purely in terms of accuracy is a bit potentially misleading, and that's what I was saying before. I feel that for very good reasons, the research community in ML is purely looking at things in terms of performance, which makes sense. But I think we need to go beyond that, and we need to look at, okay, what's its performance? Obviously, if the performance is not good enough, we don't even think about it. But if the performance is good enough, how does this interact with people? How do you present it so that it makes sense to people? And so I think we go beyond this like AI performance versus human performance.
Thank you.
So let's thank Enrico again.
Thank you.